Hello everyone. As you know, in statics, the way that we find the unknown forces, unknown reactions, and other unknown quantities is through the second law of Newton, right? Which is sum of the forces is equal to rate of change of linear momentum, correct? d over dt of m times v. And if there is no motion, right, the system is at equilibrium and the mass is constant, we can say this guy is equal to 0. So all you see we are using in statics is sum of the forces equals 0 in any direction. And for a rigid body, also, if we are dealing with rigid bodies, the other thing we can use is we say sum of the moments about any arbitrary point in any direction, positive if you consider clockwise, counterclockwise, or if it's even 3D, this should also be what? 0, because in general, this is also is equal to, let's say, for example, if it's a rigid body and I use the center of mass, so you can say, for example, this is equal to d over dt of angular momentum about the center of mass, right? Which you know this guy is equal to I times omega at I times omega, so derivative of that will be like I times alpha. And if there is no angular motion, this also is equal to 0. And not only this is valid for center of mass of the rigid body, it is valid for any other point on the 3D in the 3D space. So sum of the forces equals 0 and sum of the moments about any arbitrary point equals 0. This is all we use in statics all the time. Now, many of the structures that you see in statics, many of the problems that you might solve in statics is what we call statically indeterminate. Means the number of unknowns that you have in your problem is more than the number of equations that you can get from these equalities of 0. For example, let's say here you have the simplest 2D truss that you can have like this. So this is one member here, and then you have another member like this here, if I can draw a good one. Okay, and both of these members are pinned down to the ground like this. And here I would call the points of this simplest truss A, B, and C. So you have pin at A and C, external pins and internal pin at B. And let's say you have an external force here of 400 Newton applied to the member AB. Now here, let's say this distance between the application point of this 400 and point A, this distance here is equal to 1 meter, and assume that here the length of AB is the same as the length as BC. I also have a couple applied to member BC, and this couple is 500 Newton meter. Right, so this is my truss. And let's, for the sake of the solution, I assume that both of these are equal to 2 meters. So this force is applied in the middle of the member. Now, at the moment, these angles are both 40 degrees. Right? So this angle is also 40 degrees. And this distance, as I said, is 1 meter. So now the question is this: what is the reaction at C in the horizontal direction? So what is C at X? This is the unknown of the problem, right? And you know, in this case, there are four unknowns, two external reactions at A, two external reactions at C. And you know, in a 2D problem like this, you have two equations coming from summation of the forces along X and Y 0 and a moment about Z along about any point is 0. So in general, all you have is three equations here with four unknowns, right? And three equations and four unknowns is not going to get you all of the unknowns, right? So if we go back and look at the FBD of the combined rigid body system here, so there is no mention of the masses, so we can consider this like a truss with negligible mass of the members. So all you really have are AX and AY, as well as the external 400 Newton force. And then you have this couple here that is 500 Newton meter. And then we have the reactions at C, Cy, and Cx. Correct? So as I mentioned, definitely you only have three equations, right? Sum of the forces along X is 0, which means AX plus CX, and plus 400 is equal to 0. Then summation of the forces along Y is equal to AY plus CY equal 0. And summation of the moments about any point, let's say point A, if you consider counterclockwise positive, then you will get this 400 clockwise, so it's going to be negative 400. And the distance between that force and this point is going to be 1 meter times sine of 40 degrees. Cx has no moment, Cy does have a moment, so it is going to be positive Cy times the distance it has, which is the gap between A and C, and then finally plus the 500 couple, correct, is equal to 0. Now what's the gap between A and C? Well, here is 2 meters, this diagonal, and so each one of these portions that you see I'm drawing is going to be 2 meters times cosine of 40 degrees, right? Because the angle is 40, the diagonal is 2 meters. So it is going to be 4 times cosine of 40 degrees, right? So clearly you see I have three equations and 4 unknowns. So the problem is what we call statically indeterminate. Means using the static equations we cannot find all of the unknowns, right? So what do we do? In cases like this, we have to resort to solid mechanics and look at the deflections, let's say at C. So we set C free, we keep the rest of it and find all of the deflections at C, and then say since C is pinned down, it cannot move along horizontal or vertical direction, and then find the basically unknowns. Something similar to that we can do, which is basically the same approach, is called the principle of virtual work. What is that? It says if a system or object is at equilibrium, the virtual work done by all external forces and couples on it is 0 for any virtual motion, and motion means translation or rotation. Now, first of all, why is it that it says virtual work? Well, the reason is the system is at equilibrium. It does not move. And when that is the case, there will be no work, right? Because work happens when you have forces or couples and there is some displacement, whether linear or angular displacement. When the system is static, at the static equilibrium, there will be no motion, so there is no work. So if it is a work, it has to be virtual. You assume that the system is somehow set free from equilibrium and can do some virtual motion that leads to a virtual work. It says the total virtual work done by all external forces and couples is zero, regardless of what kind of imaginary motion, virtual motion you give to the system. So basically, another way that they show it mathematically is they say, if you want to show this mathematically, the formula you will see for it is variation of W is equal to what? To zero. So this is the principle of virtual work for static problems. Now, what does that mean? So let's say in this case, in this example, what does it mean? It means that here you can assume that the system can have any type of motion, virtual, not that it can happen in reality, because you know degree of freedom for this system is if you calculate it, you're going to see it is zero, so it cannot move. So let's say, for example, I assume that the point at C can move horizontally. Okay, so it goes from this position that it has, right? So if this is the original configuration it has at 40 degrees, now let's say it moves a little bit and now it goes to something like this. Okay? So point C has moved a little bit horizontally, and I can call it delta x of C, variation x of C, or del x of C. So is that physically possible? No, it's just a virtual motion. Now, in this virtual motion, what is the total work done by the external forces of the system on the system? We calculated, we add them all together and we set it equal to zero. That gives us an equation, and that equation hopefully can help us solve for this unknown C of x. Okay? Now, several things here. One, it says it is zero for any virtual motion. So out of all sorts of possible motions I could imagine for this system, I only chose point C to move, and I only chose it to move horizontally. Why? Because it's only in that case that this force C of x will do some work, right? This force is applied to point C. If point C moves horizontally, then your unknown force that you are after finding will do a work on it. So it will show up itself in this equation here, right? If I made point C to go vertical instead of horizontal, then Cy will do the work on that displacement, not Cx. So that kind of motion was good if you wanted to find Cy. Also, if you look at the formulation of this problem, this formulation is a variational formulation. In other words, your W here is a functional. Okay, this is a functional of what? We'll see. It is a functional of basically the displacement of point C, or you can say it is a functional of this angle alpha that each one of these members is making with the horizontal axis. Okay, so based on that alpha, or based on delta x of C, this W, which is a function of a function, it is a function of alpha, or as I said, it is a function of x of C. So what kind of solution do I have for this function in general, that if I plug this function, because they are in general functions of time. Now in this case, they are just constant numbers because it's static, but even you can use this variation later in a little bit different version in dynamics too. So alpha and xc are really functions in general. They are functions of time. And so when you put them in this function, now W is going to be a function of a function, or a functional, and you say, my goal is not really to change alpha versus time, or x of c versus time, because here your independent variable is what? t. So my goal in this variational approach is not to change time. My goal is to change what? Is to change the function inside W, the input argument to W, which is, as I said, alpha or xc. If I choose a little bit alpha different than this alpha, which you can see in this case, right? Instead of 40 degrees that I had, if I choose this alpha here, right, to be a little bit less than that. So this initial angle of it in general could be alpha. This guy could be what? Alpha minus the alpha. Or if this is 40 degrees, this initial angle, this angle here, the current angle, which you might call alpha, this alpha is what? Very close to 40 degrees. So, but with some small deviation, right? Infinitesimal change. So if I plug that, this W can change, and I say the solution is valid if you put here that makes the small change, the first variation of the work, to be 0. Please watch my video I recently posted under optimization. It's called Calculus of Variations, and you'll find all about this variational approach. So again, this is an imaginary displacement. If instead of this 40 degrees, I choose a little bit different angle, and that causes a change in W. The thing is, the total change in W, because of all forces and moments, should be equal to 0. So what does that mean in this case? Well, here I have AX, AY, CX, CY, the couple, and the 400 force. The W done by all of these guys has to be what? 0, right? The del in W. So what does that give me? Let's go ahead and see what that gives me. So first, looking at these pictures, if I say what is the work done by AX? How much work is done by AX in this virtual displacement? Well, AX and AY, both of them are applied to point A, and point A has not moved. So AX and AY will have what? No work term, right? Because the point of their action does not move. So these two will have no contribution. What about CY? Well, it is applied to point C, but C moved horizontally, and CY is vertical. You know, when a force is perpendicular to the direction of motion, it has no work. So CY doesn't do anything. CX does, right? And here we assume that delta X is to the right side, correct? So if that is the case, then the work done by X of CX is going to be CX times delta of X of point C, correct? The force and the displacement are in the same, along the same line, so cosine of angle in between is 0. Good. What about the couple? What about the 400? Well, for the 400 thing, the angle has changed, right? And if we call this change in this angle in general, this change in this angle, I call it d what? Or delta alpha, not d alpha, delta alpha, because it's imaginary. So if this small imaginary change in the angle of any of these members is delta alpha, right? So how much is the work done by the couple? Well, if you look here, as I said, the angle of both were 40 degrees. Now it's 40 minus some delta alpha. Good. So which direction did this member BC rotate? Well, the angle of it decreased from 40 to something smaller, so this member actually rotated like this, correct? In this imaginary rotation of del alpha, it is counterclockwise because the angle reduced. And the moment is also what? Counterclockwise. So you see the couple, or the moment, and the rotation are in the same direction, so it is going to be plus 500, the moment times what? The delta theta. In this case, theta is alpha, so it is del alpha, right? So del of a force in general, del W for a force is what? is the force times displacement of the point that it is acted on times what? Times cosine of angle between them. And del of a couple or a moment is what? The moment times the change in the angle, right? So these are the virtual work done by a force in a displacement and a couple in an angular rotation. So these are those two terms. And now we also have the work of that 400 Newton. Okay, so let me draw a box around this for your reference. Like that. And if you don't want to call both of these theta, I can call it beta or something. So this is the angle between force and displacement beta. This is the angle of the rigid body, the entire rigid body. So what about the 400? Well, for 400, the point that the 400 is applied to is this point here. And I can call that point something. I can call it, let's say, point D. So the 400 is moved horizontally. Point D in general does not move completely horizontally, right? Because it is rotating about point A. So point D in general moves on an arc. How much is the length of that arc? It is what? It is 1 meter times del alpha, correct? You know, if you have a circle with radius of 1 meter and this angle is del alpha, the displacement here, the length of this arc, is r times change in angle, right? And since this del alpha is very small, you can consider it to be the same as what? This chord here, basically. Now, from this displacement that you see here, let me show it with a red line. From this red line, how much of it is horizontal, right? Or, in other words, another thing you can do is, this is that force, 400. This red one is the displacement of what? Point D. Some portion of it is horizontal, some portion of it is vertical. Or you can say the work is the force times the displacement times what? Cosine of angle in between, and the angle in between is this angle here. So the question is, how much is that angle, right? If we can find that angle, that will give us the work done by the 400 Newton. By the way, in this case, actually, the member's angle is gone down. So displacement of point D is actually like this. Have to be careful, it is this way actually. Because the angle of the member is reduced. Delta alpha is like this. Okay, so this is 1 times del alpha. So the angle between 400 and delta RD is actually this angle. If you really want the angle, that is that angle that you want. How much is that angle? Well, if you look here, this chord can be considered as perpendicular to the radius, right? Or in here, the line AD, right? And the angle here that you had between this member AD or part AD with the horizontal line, this angle, was alpha. Correct? So what you have is something like this. This angle is alpha. These two lines are parallel. This one is perpendicular. So what is this guy? Right? Clearly, you know, sum of this one and the whole thing is 180. If that is 90, so this angle is going to be 90 degrees minus alpha. And it's going to be cosine of 90 degrees minus alpha. So if I want to add the term for the 400 Newton term, that is going to be what? It is going to be plus 400 times delta displacement of that point, which is 1 times delta alpha, times cosine of 90 degrees minus alpha. which, as you know, this guy is sine of alpha. Correct? And this total thing has to be equal to 0. So this is the work of 400, this is the work of couple, this is the work of Cx, Cy, Ax, and Ay has no work in this displacement. Now, the only thing that needs to be also in terms of alpha is this delta x of c. Because delta x of c also does depend on angle alpha. How come? If you remember, you can see here that the position of point C in general is 2 plus 2, 4 times cosine of the angle in general, right? So x of c in general is what? 4 times cosine of alpha. And so variation on x of c, variation x, very similar to a differential. So if you wanted to say dx of c was what? It was negative 4 sine alpha d alpha. That's the same thing. Here it's going to be negative 4 sine alpha, but variation alpha, del alpha. Okay? So this is what I need to plug into that top equation. Right? If I do everything here, what do I get? I will get Cx times a negative, or negative 4 times Cx times sine alpha, del alpha, plus 500 del alpha, plus 400 times sine alpha del alpha is equal to 0. Now here they all have a del alpha term in them, okay, which cannot be 0. Therefore the coefficient of that, which is all other terms added together, that should be 0. So it gives you negative 4 Cx sine alpha, right, plus 500, and then plus 400 sine alpha is equal to what? 0. And in this case, at this moment, how much is your alpha? Well, it is 40 degrees. Therefore, from here, you can solve for Cx, and if you do so, you will get negative 294 newtons. Yes? So you see, without me solving a system of equations, which I could not even solve. If you remember, in previous case, I showed you, you have 3 equations and 4 unknowns. It's impossible to solve for C of x. It's a statically indeterminate. But now, by this principle of virtual work, I first of all had to solve only for 1 equation and 1 unknown, and that unknown was what I needed. Right? So although the problem was statically indeterminate, but I wanted this single unknown, I could solve for it using the principle of what? Virtual work. I chose my virtual work so that my unknown gets involved in it, and all other things that are unknown, including Ax, Ay, and Cy, do not show up. The only thing that show up are the known values, and so I have 1 equation and 1 unknown, as you can see here, and I solve for my unknown. Okay, so here, to do a little bit more practice, I'm redoing this problem, but this time the question is, how much is the unknown reaction Cy? Again, if I want to go using Newton equations, I cannot solve for Cy because the problem is statically indeterminate. But this time I choose a different virtual motion, and that is to move point C vertically only. And now, in this case, the angles of the 2 members AB and BC are not going to be the same. One of them is going to be, as you can see, alpha plus del alpha. The other one goes to beta, which is related to alpha and del alpha, but it's not going to be the same as the angle of the other one. And why did I choose it this way? Because in this motion, again, Ax, Ay, and Cx will have no work. only Cy, which is unknown of interest, does have work, plus the 400 Newton and the 500 Newton meter, right? So this is what I do this time. Again, I say del W of the whole system is 0, but it is going to be Cy times delta of del of Yc plus the work of the 400 Newton, which is going to be 400 Newton times displacement of this point D times the cosine of angle between them, which we need to find, and then plus the 500 Newton times the difference between alpha and beta, correct? Right? So if alpha is bigger than beta, which means the angle is decreasing, so the angular motion of member BC is counterclockwise. That's the same direction as 500 Newton. It is going to be positive. And this total thing has to be equal to what? 0. So now the problem is first find the angle here between the 400 Newton delta R of D. Find what is delta R of D in terms of this delta alpha. And find beta as well and delta Y of C. There are several things that I have to relate all of them to this alpha and delta alpha. So what are they? First thing is, what's the angle here? Well, if I focus between at point D or on part AD, so this is AD, this is 1 meter, this is D, this is D prime, this is A. This change in angle is del alpha. The displacement of point D, delta R of D, like previous case, it is going to be 1 times delta alpha. And the force here, 400 Newton, is to the right side, like last case. And the angle I need to find is this angle here, this angle in red. It's the angle between displacement and the force. And if I look at the previous case here again, this angle was alpha. And if you remember, if I draw the extension of RD, this angle is 90 degrees. This angle, if you remember last time, the angle that I'm going to show in green, let's see if I can clean that. There we go. So this guy here that I'm depicting in green, we solved for it last time. It was 90 degrees minus alpha. And since that green angle plus the red angle, the total is 180. So the red angle is going to be 90 degrees plus alpha. So this is going to be 90 degrees plus alpha. This delta R of D is going to be 1 times del alpha, as we found it here. And this is that angle. And now we need to find this beta, and we need to find delta Y of C in terms of that alpha and del alpha. So here I call this equation 1. Now, in order to find angle beta, I use the fact that x of C and x of point C prime has to be the same, right? C only moves vertically. So x of C has to be x of C prime. X of C, if you remember, the length of each one of these members is 2 meters. The angles are alpha. So if you remember, the total distance between A to C was, if I measure it from C, correct? So x of C, if I measure it from A, this one, it was 2 cosine alpha plus 2 cosine alpha. It was 4 cosine alpha. Now, in the case of the new configuration, it is going to be 2 times cosine of the total angle, which is alpha plus delta alpha, and plus 2 times what? The cosine of beta. So can I from here find beta? Well, yes, I can. So what I need to do is I expand this cosine term, and I also get rid of a 2. So from here, your cosine of beta is going to be 2 cosine alpha minus cosine of summation. Cosine of summation, as you know, is cosine of first one times cosine of second one minus sine of first one times sine of second one. Correct? And now there is one thing that we used last time, and that is delta alpha is a very, very small virtual rotation. Therefore, the cosine of it can be approximated by 1, and the sine of it can be approximated by the angle itself. If I use this guy here, and just since it is approximately 1, I'm going to multiply this term by a 1, right? If I multiply any term by a 1, it's not going to make any difference. It's going to stay the same. But instead of 1, I'm going to multiply it by what? By cosine of delta alpha, right? If I do so, what's going to happen? This is going to be 2 cosine alpha cosine del alpha minus 1 cosine alpha cosine del alpha. So one of them will go away. And I will get 1 cosine alpha cosine del alpha. This minus and that minus will be a plus. And now if you look, this is a cosine, but the subtraction. So this is cosine of alpha minus del alpha. So cosine of beta is equal to what? Cosine of alpha minus del alpha. Therefore, your beta can be said to be what? Alpha minus del alpha. So this is equation number 2, right? Or basically, if you want, let me put 2 to be something else. If I want, since I'm after alpha minus beta, from here, alpha minus beta is going to be del alpha. How about that? That directly can go into this equation, and here you replace it with del alpha. And finally, I need the vertical displacement of y of c in terms of everything else. So del y of c is y of c prime minus y of c. C is at the horizontal level, it is 0. So it's only y of c prime. And y of c prime is as much as you go by AB upward and as much as you go by AC prime downward. So it's the y of AB, actually that point is B. Y of AB is 2 times sine of total angle of the left member. So it is 2 sine of alpha plus del alpha, then minus 2 times sine beta. And again, here for beta, I'm going to plug this relation that I found down here. So it is going to be, if I factor a 2, it's going to be sine of alpha plus del alpha minus sine of alpha minus del alpha. And if you know summation of sine of the summation of 2 angles or subtraction of the 2 angles, this is going to be sine first one cosine second one plus cosine first one sine second one. This is sine first one cosine second one minus, right, sine second one cosine first one. And when you subtract, one of the terms is similar, the other one is not. So you will get 2 times cosine alpha sine del alpha. This is the term that is not the same in each, and in the first one is positive, in the second one it is negative. You get 2 of that, times 2, you get a 4 actually. So it is going to be 4 times that, or 2 times that basically. And remember, the alpha is a small angle. Sine of it is the same as the angle itself. So here I can refer to what I found earlier, which is this guy. If I use this and bring it all the way to here, it gives me that delta y of c is gonna be 4 times cosine of alpha del alpha. And this I can call 3. Now if I plug 3 and 2 into 1, I will get what I need. So 2 and 3 into 1, that means cy times delta y of c, then plus 400, and as you know, cosine of 90 degrees plus angle is negative sine of the angle. So this is going to be negative 400 sine alpha del alpha. And the last one is 500 del alpha. This whole thing has to be 0. Again, you see they all share a del alpha, which cannot be 0. So we simplify, and you will get one equation in terms of the unknown cy, which, by the way, if you solve for, you will get negative 79.3 Newton. So again, you see, I could solve for one other unknown reaction without the need to go through all of those equations that at the end of the day cannot even give me this unknown because the system is indeterminate statically. So here I solve for 2 unknown reactions using this virtual work, and hopefully this video was a good introduction to this important principle to you and how to use it for solving statics problems. Thank you. See you in my next video.